All right, so I'm going to assume again that you have some familiarity with phasors, but I will go back and review whatever you asked me to review, so we're not going to start completely from scratch. What I plan to do today is, since it's the first lecture, I'll go over the node voltage and the loop method as it applies to phasors. I'll also look at a few things like Thevenin equivalence, and in the process go over these little things that make a lot of difference when it comes to exams, like how do you deal with controlled sources, how do you set up things in terms of the power balance, although the power balance is probably going to come in my next lecture, but perhaps if we're really fast today, which I don't really encourage, but if you're deadly bored with what I'm doing, tell me to speed up and skip the problem, and we can move on to that as well. But my primary objective today is roughly half the time we're going to be practicing the node voltage method, and the other half the loop method as it applies to phasors. Okay, so let me start with the following problem. And this one is fairly straightforward. So here's the circuit that we're going to look at. A resistor, an inductor, a voltage source, and current source. So we'll put in some values. Equal, R will be 1 ohm, L will be 1 Henry. EG will be a sinusoidal source, so it's 2 cosine t, and IG will be sinusoidal as well, 5 cosine t. So what I'll be interested in are the nodal voltages in their steady state form. When I say steady state, that means after a sufficiently long time. Hopefully you remember from whenever you took your previous circuits class that in any kind of circuit involving inductors and capacitors, it takes a while for the system to settle down into what's known as its steady state. So it's going to bounce around a little bit, but after a sufficiently long time, you will reach a steady state where all the currents and voltages will be sinusoidal with the same frequency as your sources. And your sources both have the same frequency. This here corresponds to 1 radian per second. So both sources are like that. In general, I will keep it that way. I will not mix frequencies. If that ever happened, you could use superposition and break the problem up into several parts and add them up. But that's not really what we're interested in. So how does one deal with problems of this sort? Well, first and foremost, when you're dealing with any kind of phasor problem, you want to redraw the circuit in a phasor format. What that means is that you'll keep the resistor as it is. You will replace the inductor with its impedance, which is J omega L, and you will replace the two sources with their corresponding phasor values. So what does that mean? Well, this is the part where I'm going to call upon your memories from ELEN 50. When you're given sinusoidal quantities like Vg of t and Ig of t, you can always uniquely associate a complex number with them, which we refer to as a phasor. And you do that by creating the following. The phasor that corresponds to Vg of t will be a complex number whose magnitude equals the amplitude, so 2, and whose angle equals whatever angle you have here, which in this case is 0. If you had t equals 45 degrees or something like that, that angle would show up over here. We'll have some problems like that. Now, for IG, we do the same thing. And the magnitude is 5, the angle is 0. So, in effect, the phasors that correspond to the voltage and current source are real numbers because their angle happens to be 0, which will always be the case if you have no phase angle in the sources. Let me put on this mic and see if that sounds better. Okay. All right. So what do we do from here? Well, the node voltage method, which is the first thing I'm going to look at, is going to require us to pick certain directions for our currents. Where we have sources, these directions are applied by convention. So for a current source, we'll pick that direction. For a voltage source, as a matter of convention, we'll go from plus to minus. For the inductor and the resistor, we can pick whatever we like. So let me do this. Now the idea behind the node voltage method is to declare one node as the reference node, one at the bottom, and then label the voltages associated with all the other nodes in order. You may recall that a nodal voltage is really the voltage between a particular node and the reference node. When you're talking about voltages in principle, a voltage is always between two nodes. But if one of them is implicitly assumed to be the reference node, then you can actually associate voltages with individual nodes, knowing that the second one is the reference node. So V1 is really the voltage between this node and the reference node, and V2 the voltage between this node and the reference node. And that's what we're going to try to find here. Once we find them in phasor form, once we get those complex numbers, we're going to convert them back into the time domain using this relationship between the polar form of complex numbers and sinusoids. Are we okay so far? Any questions? This should all be reasonably familiar, but don't be shy, ask. That's what I'm here for. All right. So with the node voltage method, what you do is you write Kirchhoff's current law around each of the nodes, except, of course, the reference node. So in this particular case, we have two equations by Kirchhoff's current law. The first one on the left, I'll call this current here. Let's give it a name. Let's call it I1. Like the type of symbols. So what we're going to have here is I1 going out, so coming with a plus, and IR going out as well. That's the convention that I like to use when I write Kirchhoff's current law. So if a current goes out, then you take it with a plus. If it goes in, and take it with a minus. All right, for node 2, what we're going to have is more of the same, essentially. This current is going into the node, so you've got minus IR. IL is going out. And IG is going in. And those are my two basic equations, which I can write by Kirchhoff's current law. Once I have that, my idea is to express each one of these currents, if I can, in terms of nodal voltages, either based on Ohm's law or something like that. So I'll line them up over here. And see what I can do. And the first one is actually a trouble. because I don't have anything like Ohm's law to relate I1 to any of the nodal voltages. So what we do in such cases, and you'll find that this is typical of voltage sources, whether independent or controlled, is that we can't express their current in terms of nodal voltages, so I'll leave it as a question mark for now. We'll figure out what to do with that in a minute. For IR, it's quite straightforward because that one sits between nodes 1 and 2, and the current is assumed to go from 1 to 2, so you can rewrite that as V1 minus V2 over R. And we do something similar for the inductor. Again, as you know, with impedances, you can pretend like it's a resistor with a complex value. So the current, as specified over here, would be V2 over J omega alpha. And IG is not a problem because it's actually something that's given, so I can immediately replace it with a 5. So I've been moderately successful here. I managed to get 3 out of 4. But I1 is still a problem. Now, whenever that happens, and it will every time you have a voltage source, you lose the equation where that quantity shows up. And you have to come up with a different one, so-called compensated equation, where you rely on something other than Kirchhoff's current law. Now, with voltage sources, you always know something that hasn't actually been used. In particular, because you have this voltage source sitting here between node 1 and the reference node, you could say that V1 equals Vg. And that's a legitimate replacement for this first equation. So you can say V1 equals Vg, and phasor Vg is a 2. That's a perfectly legitimate equation involving one of the nodal voltages. It's a trivial one because that voltage happens to be 2, but it's an easy equation. There's nothing wrong with it. For equation 2, what you have to do now is plug in what you have over there on the right. So I'll call it 2 prime, and 2 prime has minus IR, so minus V1 minus V2 R plus IL minus IG equal to 0. These two are my basic equations here, and from them I can actually calculate V1 and V2. I have 2 equations in 2 unknowns, V1 and V2. All I have to do is sort out these equations a little bit so that I can then put them into matrix form, and I will insist on doing things that way, because without matrices you are in deep trouble here. When I throw things at you on the midterm, I will easily give you 3 or 4 equations, and doing that manually is not something that you would wish upon your enemy. You really don't want to do that. So you can bring your calculator or MATLAB, your laptop, whatever you like to use to deal with matrices that have complex numbers in them. All that is fair game. All my tests are open book, open notes. You don't have to worry about that. I'll show you how to do this in MATLAB if you have no experience with it, but you're welcome to use any other software or calculator. Some TFs will do it. So, now that we have these 2 equations, I can sort them out specifically. We will get the eraser. I can now get rid of these 2 and rewrite my node voltage equations in the following way. Let me take this one first. So next to V1, I have minus 1 over R. Next to V2, I have 1 over R plus 1 over J L. And on the right-hand side, there's a 5. And this is my second equation. V1 equals 2, 2. I grant you that you could easily solve this by substituting 2 in there and computing it that way, but I really want to make it a habit to deal with these things in terms of matrices. So even though it's a trivial thing, we will go through that exercise. Before we do that, we need actual numbers. So I need to plug in the values here for R and L. And I've got everything here. R is a 1. So this here is a 1. Here I'm going to have 1 plus 1 over j omega L. Omega is whatever multiplies t, which is a 1. L is a 1, so this becomes 1 plus 1 over j. What is 1 over j? You don't want j in the denominator. What is j? It's minus j. So if you're ever in doubt, 1 over j, multiply up and down by j, and you get j over j squared. J squared is minus 1. So this becomes 1 minus j. And we're now more or less foolproof. So all I need to do now is put this into matrix form and solve. So my 2 unknowns will be 1 and 2. First equation is minus 1 times v1 plus 1 minus j times v2 equals 5. The second equation, v1 times 1, nothing times v2 equals 2. And that's what you have to solve. Now at this point, you can plug this stuff in to your calculator or to MATLAB. Simply ask it to solve, and here's what you're going to get. This is what I need my notes for. Because I don't know that off the top of my head. Well, V1 is going to be equal to 2, obviously. V2, which is what I'm interested in here, is 3.5 plus j 3.5. That's what MATLAB is going to give you. Do you want to keep it in that form? Can you immediately translate this into sinusoids? Not in this form. You need it in polar form. So what you need to do is convert this complex number in Cartesian form into the polar form. Are you all familiar with that? If you want to take a step back and remind you how that works. I don't know. But I don't want to waste your time. The polar form here, let me do that just for the sake of completeness. I'm not going to fuss too much about it, but I will remind you that complex numbers can be represented in 2 different ways. So if this is a complex number sitting here in the complex plane, one way is to represent it in terms of its 2 projections onto the real and imaginary axis. So one way is to say that x plus jy equals z, where this is known as this real part and this as the imaginary part. That's the so-called Cartesian form. Alternatively, we use the polar form, which looks at the distance to the origin. Magnitude z, that's the magnitude of this complex number, and the angle. And the way we write z in polar form is as magnitude z e to j theta. What I've been doing here is a shorthand where instead of saying e to the j theta, we just label it this way. But that's what it's supposed to be. So converting from here to here is really a matter of simple trigonometry. So if you have a Cartesian form and you're looking for magnitude z, you've got a right triangle here, so magnitude z would be square root of x squared plus y squared. And this angle would be related to x and y in the following way. So just take the inverse tangents of that and you get it. That's how one converts a Cartesian number like this into polar form. And when you do it here, you get 4.95, angle 45 degrees. And now we're done, because now we have a pair of numbers that we can directly translate into sinusoids. So remember that our frequency here was 1 radian per second, so that's going to be the case across the board. This one has angle 0. So you can say that v1 of t is 2 cosine t, and v2 of t, 4.95 will be the amplitude, cosine t plus 0.5. And these two are so-called steady-state values, meaning that after a sufficiently long time, that's what you're going to see in your circuit. But again, I emphasize the difference between the complete response and the steady-state response. Phasors don't tell you what happens in the transient period. They just tell you what you're going to end up with. With the transient, you'll need Laplace transforms, and we'll talk about that in the second half of this course, but not yet. So phasors are a powerful thing, but they don't give you the whole story. They give you the steady-state response, and that response is an important thing. That's how many circuits are designed to operate. That's how power systems are designed to operate. So it's not like it's not an interesting thing. The advantage of phasors, of course, is that you don't have to solve differential equations. Everything that I've done so far is algebra, and it will remain algebra as long as I'm interested in steady-state response. So this is basically what the node voltage method boils down to. So what I suggest we do is I'll go over a couple of additional problems and kind of make it a little more difficult and interesting. I'll put in things like controlled sources. We will look at Thevenin equivalents and things that are associated with that. Make the whole thing messier, but since we're dealing with matrices, that really doesn't matter too much. Do you have any questions about this? All right, well, look at another example here. All over the place. So this is the circuit which we will look at. It's not resistive here, not an inductor. Again, I'll give you specific numbers. Usually I'll keep them easy. I'll use things like 1, 2, typically, with these values. However, non-physical that may be, because here I'll have C equals 2 farads, which is huge capacitance. So I wouldn't expect something like that in a practical circuit, but the algebra works out well out. And my VG will be 5 cosine sine t. And again, what I'm going to try to do is go through this node voltage procedure and for all the steps that we've done so far.
I think it was 2/3 and then you got 2.
No, I meant to say 2. It is supposed to be 2. I was just pointing out that 2/3 is a lot for a circuit like this. And one of them is actually the stuff. If you actually wanted a physical circuit that does something meaningful, you'd be looking at kilo ohms, microfarads, but then the math of it would be very limited. And we're right now more interested in that than anything else. So our first step, as always, is going to be to convert this into a phasor circuit. And I have a habit of labeling every point where 2 or more elements meet explicitly with a node. This will be my reference node. And then I need to convert this into an impedance. So this becomes J omega L1. This becomes J omega L2. For capacitors, the impedance is 1 over J omega C. So it turns into this. And VG becomes this. So now we're set up for phasor analysis because you can now treat every one of these impedances as if it were a resistor. So everything that you're comfortable doing with resistors, you can do with these numbers as well. The only difference is that they're complex. We need to pick directions, and the only convention that we need to abide by here is plus to minus 4 voltage source. You'll see why that's the case down the line because it makes it more convenient. But as a matter of convention, just stick to that. Where you have other elements like inductors and capacitors and resistors, you basically pick whatever you like. So let's say this, 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 this. Okay. So in this case, we have 3 nodes plus the reference node. So we're going to end up with 3 node voltages. V1, V2, and V3. And every one of them, as I mentioned earlier, is really the voltage from that node to the reference node. But it's much more compact and just associated with individual nodes. And what I have to do now is write out Kirchhoff's current law around each of the 3 nodes. And that shouldn't be too hard. That'll give me 3 equations to work with. I will label this current that flows through the voltage source with I1 again. And with that, I can now start writing the equations. My first one, for this node to the left, for node 1, is going to be I1 plus IR equal to 0. My second one, we've got IR coming in, so there's a minus here. IL1 going out. And IL2 going out. And then finally, node 3 minus IL2 plus IC equals 0. So those are my 3 basic equations that follow from Kirchhoff's current. And what I'll do now, as I did before, is I'll line them all up on the right-hand side and try to express every one of these currents in terms of my node voltages. And if I can do that, I'll get 3 equations in V1, V2, and V3, which is exactly what I need. So let me list them. And again, right off the bat, I have a bit of a problem because I cannot express the current of the voltage source in terms of other voltages. That's because I have nothing like Ohm's law for this type of element. Instead, I have to leave it as a question mark, and I will lose the corresponding equation when it comes to that. But let me first express the other currents, starting with IR. That would be V1 minus V2 for R. IL1 would be V2 over J omega L1. IL2, given the direction, would be V2 minus V3 over J omega L2. And finally, IC. Now here you've got V3 over 1 over J omega C, so that's effectively J omega C times V3. So I was able to get rid of all of them except for I1, which means that I lose equation 1. In its place, as in the previous example, I do know that the voltage between node 1 and the reference node is actually equal to Vg, and that gives me a compensating equation, which I can write as V1 equals Vg. And as soon as I figure out what that phasor is, I can put in a number there. Remember how that works. The phasor associated with this sinusoidal source is a complex number whose magnitude equals the amplitude, so it's 5. And whose angle is whatever angle we have here, and that happens to be 0. So that's a real number. And therefore I have a 5 here. So I made up for that lost equation. Okay, so far? Quite perhaps I'm going to prompt you every now and then, just to make sure we're on the same page. All right, equations 2 and 3 have no question marks there, so all I have to do is substitute. Oh, was that at the beginning of the question?
Yeah, with the IC, I was wondering if you shouldn't, with the equals R, and then we're 1 over.
It's 1 over, yeah, exactly. So that's why it ends up being ultimate picture. So this one, when we plug things in, is going to give me minus IR. And here you need to be patient because it's easy to make a mistake. So if you go at the same pace that I do when I'm doing this on the board, you're fine on the test. Believe me, you're going to lose an extra minute or two, but then you'll save yourself half an hour of debugging in the process, which is always good in the test. So minus IR plus IR1, which is V2 plus IL2, which is V2 3 over J omega L2 equals 0. And then equation 3 prime, where I substitute IL2 and IC, so minus IL2 minus V2 minus 3 over J omega 2 plus IC, J omega C 3 equals 0. So now I've got all three equations. They're kind of scattered, and the second and third one need to be sorted out. But by and large, I have what I need, so I can now erase my circuit and use the piece of the board. Sort these equations out. First one is trivial. just V1 equals 5. Second one, next to V1, there's only one term, minus 1R. It's a good idea to sometimes put a little half a break to make sure that you don't skip any terms. Next to V2, we've got, again, 1 over R, and this one, and you have 1 over J omega 1. And 1 over J omega 2. And then the last term, minus 1 over J omega 2, 3 equals 0. And actually, let me do these here. Last equation, there's no V1. There's one term next to V2. Minus 1 over J omega L2. And then next to V3, we've got J omega L2 plus J omega C. So those are my 3 equations, which are almost ready for processing. All I have to do is plug in the values, and then I'll be able to put them into matrix form. It will be fine. So when you look at these values, R is 1. So this turns into a 1. This here, R is 1. Omega, which you find as the multiplier to T, is 1 again, conveniently. L1 and L2 are both 1, so I've got plus 1 over J, plus 1 over J. And this guy is 1 over J. And again, I'll remind you that 1 over J is the same thing as minus J. This becomes 1 minus 2J, and this becomes minus J. Same thing here. This is 1 over J, which is the same thing as minus J. This is 1 over J. Now C is not a 1, C happens to be a 2, so this will be plus J2. And when you recognize that it's a minus J, open a J. So we can now put this in matrix form. First equation. So the first one has 1 times V1, nothing times V2, nothing times V3, and the 5 on the right hand side. The second one has minus 1 times V1, then it has 1 minus J2, times V2, and this minus J and this minus sign will give you a plus J. And there's a 0 on the right hand side. Here you have a similar situation. This minus and this minus cancel each other out. So you've got nothing times V1, J times V2, and then out of this whole thing, you've got another J times V3 equals 0. I've dumped this to MATLAB or whatever other software you're using for this, and when you solve, here's what you can get. We'll just double check my work, because I make mistakes too. this seems to be okay. So when you solve this for V1, you get 5. For V2, you get 0.5 plus J 1.5. And for V3, we get minus that. So it happens. So at this point, you've solved your node voltage equations. And the only thing left to be done, again, is to convert this to polar form. And once you have that, you'll get everything as sinusoids. This one is trivial because it's zero angle. Here, when you convert, you get magnitude equal to 1.58. The angle is 71.6 degrees. And you really don't have to be that precise. I just copied how that gave it. This is 72 would be okay in my book. Here you get the same magnitude. The angle will be different because of these signs, and it will be minus 108.4 degrees. They're off exactly 108 degrees. This is the negative of the other one. It's a good idea, and I would strongly suggest this, that when you practice these things, go over every single problem I did in class, see if you get the same answer. That's one of the reasons why I'm putting it all on the board, so that you can actually check it. That's the point. All right, so now that I have that, my steady state voltages are going to be V1, 5, cosine T, V2 is 1.5 cosine T plus 71.6 degrees, and V3 1.58 cosine T minus 100. And with that, we finish this one. Yes, ma'am.
I probably asked this earlier, but quick kind of review on the sign convention for the currents. When you're doing the current from V3 to the reference node, if we put the voltage going the other way, like facing V3, it would have been negative, right? Off the sign.
You mean when there was a capacitor there, right?
Yeah. So if we had it going into the node, it would have been negative instead of positive.
Well, remember this, that when you're dealing with node voltages, and this is V3 and this is the reference node, it's implied that this is the polarity of V3. The reference node is always the one with the negative polarity, and the node is the one with the positive. So you don't actually have a choice.
Yeah, okay.
Do you have any other questions before I get into Thevenin equivalents? Thevenin equivalents are a little trickier, and that is something that you might have seen in a slightly different format. So I'll do that carefully. They are important in the world of phasors just as much as in DC circuits. And they'll also give us an extra chance to practice the node voltage method, because at the end of the day, the Thevenin equivalent boils down to the node voltage method. But let me remind you of how that works. And what the idea is. Many times, you have a large chunk of your circuit that is either known or not likely to change or not interesting to you, and then a smaller piece that you are interested in. A typical example of this arises in power systems when you want to analyze in detail the behavior of a relatively small geographic area, which happens to be connected with the entire country. Instead of having to solve the entire US network, it would be very much to your advantage to simplify what's not of interest and then focus on this little area, say, let's say New England or whatever, that's of interest to you. And Thevenin equivalents would let you do something like that because they would represent, in theory at least, the entire network with an equivalent impedance, which we label Z Thevenin, and an equivalent voltage source, V Thevenin. And that then simplifies the circuit dramatically because you have only two elements and you can model this in much greater detail, not worrying about how many nodes were in here. This is also interesting if the smaller part of your circuit changes over time, which happens in power systems because demand varies, so you think of that as something that fluctuates periodically. So instead of you having to solve the whole thing every single time this changes, you just solve a simplified circuit because this, and this could be, for all you know, the entire US west of Massachusetts. That's a huge circuit. When you simplify it to something like this, you really have a much more manageable problem. That's why we do Thevenin equivalents. Now, I will point this out. Thevenin equivalents are always kept in complex form because a Thevenin equivalent is generally never the end of your problem. You usually have something more to do. It's their simplification. So you don't want to convert V Thevenin into a sinusoidal form right now. That's something that you don't care about. You will keep both V Thevenin and Z Thevenin as complex numbers. When you're done with all your calculations, then you will convert whatever currents and voltages you're interested in into sinusoids, but not in the Thevenin stage. So the question then is, how does one find V Thevenin and Z Thevenin? There are two different procedures. So it amounts to solving your circuit twice, which is a fair amount of work, so it better be worth your while. For V Thevenin, what you need to do is basically disconnect whatever was hooked up to the part which you want to simplify, and simply calculate the voltage at these terminals, the so-called open circuit voltage. That's your V Thevenin. So basically take a pair of scissors, cut everything off, and solve what's left to find V Thevenin. That boils down to a no voltage problem, essentially. For Z Thevenin, it gets a little trickier. Because you initially do the same thing, you remove whatever was hooked up here, but now you replace it with a current source, whose phasor is magnitude 1, angle 0. And I put this angle 0 to remind you that that is actually a sinusoidal source, not a constant source. It's 1 cosine omega t, whatever it is. Now, very importantly, you have to transform the circuit here in the following way. Eliminate all independent sources, while keeping control sources where they are. Do not touch control sources. That gives me a fit. If you want to lose points on the midterm, then by all means tamper with control sources and do impedance. But you're not supposed to touch them. Only independent sources are effective. And by eliminating, that means if you have a voltage source, you simply short it out, turn it into a piece of wire. If you have a current source, you open it up. If this is VG, and this is IG, this would correspond to setting VG equals 0. It's just a piece of wire, and this would correspond to no current. So what you effectively have to do here is short out all your voltage sources that are independent, open up all your independent current sources, and don't touch control sources. Yes?
Would it effectively turn control sources to zero?
No. No, because you have this guy,
So
which powers them.
So that control source could be based off of whatever that particular current?
Well, if the control source were controlled by the current of an independent source, then that would be the net effect. That rarely happens, though. But yeah, it could end up being zero, but you can't throw it out of the circuit a priori. That would have to come out of your calculations, as you'll see. So theoretically, it could happen. All kinds of things could happen theoretically if they don't actually happen. This is one of them. So, with that in mind, our next problem is going to be a Thevenin equivalent, which will involve solving the node voltage equations twice. Once for V Thevenin, once for V Thevenin. And as I said, because it's twice the work, it better be worth your while. And it is worth your while. If you have something that changes 500 times, you don't want to solve the whole thing 500 times. You're better off solving it twice and then solving the simplified thing 500 times. You could easily imagine a scenario where what you had here was a time-varying impedance. If you simplify this, the Thevenin equivalent, you actually don't even have to solve anything. You get yourself a simple formula with that time-varying impedance, whereas solving it again and again and again every time this thing changes is very